Hey there, welcome. Let's start with something you've probably tried before, picking up a magnifying glass and looking at a page of tiny text. Suddenly, those small letters seem so much bigger and clearer. That effect is what we call linear magnification. Linear magnification is simply the comparison of sizes. It tells us how much larger or smaller an image looks compared to the actual object. In physics terms, it is the ratio of the height of the image to the height of the object. The formula is straightforward: m equals image height divided by object height. This value, the magnification factor, helps us understand the scale of the image produced by a lens. If m equals 2, the image is twice as tall as the object. If m equals 1/2, the image is only half as tall. Think about it in real life. A magnifying glass lets you read small print by producing an image that is larger than the letters on the page. Jewelers use the same principle to inspect the fine details of precious stones. All right, now that we know what magnification means, let's dig a little deeper and actually derive the formula for it. Imagine an object placed in front of a convex lens. The distance of the object from the lens is denoted by u. The distance of the image formed on the other side is denoted by v. These two distances, object distance and image distance, are the keys to our derivation. So, magnification can also be expressed as the ratio of image distance to object distance. In other words, m equals v divided by u. This tells us how much bigger or smaller the image appears compared to the object. If v is larger than u, the image looks magnified. If v is smaller, the image looks diminished. Now, how does this connect with focal length? For a thin lens, the relationship is governed by the lens equation 1 by f equals 1 by v minus 1 by u. By combining this with our magnification definition, we can see how the size of the image depends not just on distances, but also on the focal length of the lens. As you can see in the diagram, rays from the object bend through the lens and meet on the other side to form an image. The distances u and v are clearly marked, helping us visualize the relationship. So, to sum up this step, magnification is not just about comparing heights, it's also directly tied to the geometry of the lens system, the object distance, image distance, and focal length all working together. Hello everyone! Have you ever used a magnifying glass to look at the fine details of an insect or to read really tiny text on a label? The image suddenly looks bigger, clearer, and upright. That's a perfect everyday example of positive magnification produced by a convex lens. Now let's understand how it works. A convex lens can actually form two kinds of images depending on where the object is placed. If the object is far away, beyond the focal point, the lens forms a real and inverted image. But if the object is placed closer to the lens than the focal point, something interesting happens: the image becomes magnified and upright. In physics terms, this is called positive magnification. The formula shows that magnification m equals v divided by u, and in this case, m is greater than 1. That means the image is larger than the object. As you can see in the ray diagram, rays from the object diverge after passing through the lens, but when extended backward, they appear to meet on the same side of the object. That's how a virtual, magnified image is formed. And here's the beauty of it: this principle is exactly what makes magnifying glasses so useful for examining small insects, reading fine print, or inspecting tiny details in engineering work. So remember, when an object is placed within the focal length of a convex lens, you get a magnified, upright, virtual image. That's positive magnification in action. Hello everyone! Let's shift our focus now from convex lenses to concave lenses. You may have seen these in spectacles used by people with myopia, or nearsightedness. The lenses look slightly hollow at the center and thicker at the edges. That shape gives them very different behavior compared to convex lenses. A concave lens always produces a diminished, upright, and virtual image of any object placed in front of it. No matter how close or far you put the object, the image is always smaller and appears on the same side as the object. This is why we say the magnification for a concave lens is negative and always less than 1. Mathematically, m is less than 1. That means the image height is smaller than the object height. Unlike convex lenses, concave lenses can never give you a real image on a screen. As you can see in the ray diagram, when parallel rays pass through a concave lens, they spread out or diverge. If you trace these rays backward, they appear to meet at a virtual point behind the lens. That's where the smaller, virtual image is formed. In real life, this principle is incredibly useful. Concave lenses are fitted into glasses to correct myopia. They make distant objects appear smaller but clear, allowing the person to see them properly. So, remember this simple difference: convex lenses can magnify and even form real images, but concave lenses always shrink the image, giving a virtual, upright, and diminished version of the object. Alright friends, let's put everything we've learned about magnification into practice with a worked out example. Here's the problem: a convex lens has a focal length of 20 centimeters. An object 5 centimeters tall is placed 30 centimeters away from the lens. We need to calculate the magnification produced by the lens and also find the size of the image. Step 1. We begin with the lens formula. That is, 1 by f equals 1 by v minus 1 by u. Here, f is 20 centimeters, u is minus 30 centimeters, and we need to solve for v, the image distance. Substitute the values: 1 by 20 equals 1 by v minus open bracket 1 by minus 30 close bracket. This simplifies to 1 by 20 equals 1 by v plus 1 by 30. Rearranging, 1 by v equals 1 by 20 minus 1 by 30. Calculating this gives 1 by v equals 1 by 60. Therefore, v equals 60 centimeters. Step 2. Calculate magnification. Magnification m equals v divided by u, that is 60 divided by minus 30, which gives m equals minus 2. But remember, this minus sign shows the image is inverted. The magnitude 2 tells us that the image is twice the size of the object. Step 3. Let's find the image height. Magnification m equals image height divided by object height. Substituting the values, minus 2 equals image height divided by 5. Therefore, the image height equals minus 10 centimeters. Negative height indicates the image is inverted, and the value tells us it is 10 centimeters tall. So, the final answer: the image formed is real, inverted, and magnified twice the size of the original object. As you can see, every step of the calculation links back beautifully to the lens formula and the definition of magnification. This is exactly how numerical problems in optics are solved: neat, logical, and directly connected to real-world lens behavior. Alright friends, let's take a moment to wrap up everything we've learned about linear magnification. Linear magnification is a simple yet powerful idea in optics. At its core, it tells us how the size of an image compares to the size of the object. Whether the image appears bigger, smaller, upright, or inverted, all of it comes back to this single ratio of image size to object size. But it's not just theory. Magnification has countless applications in our everyday life. From something as common as a magnifying glass to advanced instruments like microscopes and telescopes, all of them rely on magnification to make the invisible visible and the distant appear close. And if you think about it, this concept surrounds us everywhere. The spectacles you wear, the camera on your phone, even the telescope used to explore faraway galaxies, they all use the principle of magnification to alter how we see the world. So, to sum it all up, linear magnification is the bridge between physics and perception. It explains how lenses change what we see and why devices from eyeglasses to cameras work the way they do. I hope this journey through magnification has given you not just formulas, but also an appreciation for how physics connects with our daily experiences. See you next time with another exciting concept of light and optics.